In this video, we're going to quickly explore some applications or uses of the dot product. First off, we're going to look at how the dot product might materialize and compare this v1 times v2 times v3 with this v1 times v2 times v3. And ask yourself first whether those are equal or if they're different and why. Take a moment and then we'll check in. All right, what we're looking for here is both of these in some sense are true, but I think C describes the scenario more correctly. If we take v1 times v2, that is going to be a scalar. Let's go back. I'm going to go put this down here. If we take our left-hand side, that is v1 times v2, but as a dot product, and so that's going to give us a scalar value. If we then multiply that by v3, this is going to be a vector in the direction of v3. We're going to have some multiplier times the vector v3, and that's going to be a certain direction. If we compare that with the right-hand side, here we have v1 first times v2 dotted with v3. The dot product is going to turn these two into a scalar. And so this right-hand side is going to be a vector in the direction of v1. And of course, there's no reason why v1 and v3 would have the same direction to start with. So if we compare those two, these are not equal in general. Going back to the statement here, the issue is that the product of v1 with v2 versus v1 of v2 here is different because we're doing a dot product in one case and a scalar product with this combination here in the second case. Another interesting application of dot products is again combining the dot product with components with the dot product with the angle definition. And what we can do is look at three vectors, say here, in 3 dimensions, which is harder to visualize, and we can ask about the angle between them. Now we know already that if we have non-zero vectors, and all of these are non-zero, and we take the dot product, if we get a 0 dot product, then the vectors are perpendicular. So let's do a quick calculation of these dot products. A dotted with B is going to be 1 times 1 plus 0 times 3 plus negative 2 times 0, and that is going to equal 1. Let's do all these calculations in advance and then we'll analyze them. If we take A with C, that'll be 1 times 2 plus 0 times 1 plus negative 2 times 1, and that is 2 minus 2, that is 0. So we can already see one perpendicular combination. And last but not least, we have B times C, 1 times 2, 3 times 1, and 0 times 1. And that would be equal to 2 plus 3 is 5. All right, now we associate that back to the angle definition of the dot product. So in this case here, A dotted with C is what we started with. We got a value of 0. And what we ended up with was a 0 value equaling the alternative definition. Here we have positive quantities for both these two lengths. So that means this last term here, this cos theta must equal 0, which implies that theta has to be pi over 2, or the A vector has to be perpendicular to the C vector. So these are perpendicular. That decomposition using the angle formula can give us another insight. If we do the same calculation here, A dotted with B, the other way we can write that is, again, with a cos of the angle between them times the length of A and B. And if we look at the signs of everything involved here, we have a positive quantity for the dot product. Lengths are always positive. And so that means this cos of theta must be positive as well. Now let's think about that for a moment. If we talk about the cos graph, we talk about angles, The coast graph starts at 1, goes down at 90 degrees or pi over 2 radians, it hits 0, and then it goes negative. If that's the case, then if we're going to have a cos of an angle and it's going to be positive, the only way to have that happen is to have a theta in this range here. And that answers our question here. What can the angle be between these two vectors? Well, it has to be an angle of less than 90 degrees. Or less than pi over 2 radians. And that result comes from this dot product being positive. If this were negative, then the cos theta would have to be negative, and that would put us into this range of the angle and cos relationship, cos theta negative. So the sign of this dot product will tell us whether we have an angle that's less than or larger than 90 degrees or pi over 2 radians. For this example down here, we can now conclude that this dot product is positive, and that means immediately, again, that there's an angle less than pi over 2 between the vectors b and c. And note that that is not obvious at all in three-dimensional vectors. We don't have an easy way to visualize those and be able to imagine the angle between them. So this is quite a powerful technique that generalizes to vectors that we can't draw easily.